To explain the metal-to-ligand bonding in complex compounds. Different theories, such as the valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory were proposed. Among these theories, the valence bond theory is the simplest, which satisfactorily explains the structure and magnetic properties of a large number of coordination compounds. The valence bond theory was proposed and developed by Linus Pauling. Here are some salient features of the theory. The central metal atom, or ion, has the required number of vacant orbitals for accommodating the electrons, donated by the ligands. The number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex. The vacant orbitals of the metal atom or ion undergo suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. The geometry of the complex can be predicted based on the coordination number and the hybridization of the metal atom or ion. As you can see from the table, when the coordination number is 4, the metal atom or ion may undergo either sp3 or dsp2 hybridization, and the complex may assume either tetrahedral or square planar geometry. When the coordination number is 5, the metal ion undergoes sp3 dehybridization, and the complex has trigonal bipyramidal geometry. When the coordination number is 6, the metal ion may undergo either sp3d2 or d2sp3 hybridization. In either case, the complex has octahedral geometry. A ligand orbital containing a lone pair of electrons forms a coordinate covalent bond by overlapping with the hybrid orbitals of the metal ion. The magnetic moment of the complex can be used to determine its geometry. Note that the magnetic moment of coordination compounds can be measured by magnetic susceptibility experiments using a Gauss balance. The results of the experiments can be used to work out the shape of the complex. In the formation of a complex, if the metal utilizes its inner d orbitals, then such a complex is called an inner orbital complex or low spin or spin paired complex. On the other hand, if the metal utilizes its outer orbitals for complex formation, then such a complex is called an outer orbital complex or high spin or spin-free complex. Now let's apply these postulates to a dimagnetic complex, hexaamine cobalt 3 chloride. The cobalt atom in its ground state has the electronic configuration of argon 3d7 4s2. In the given complex, the cobalt is in +3 oxidation state. Thus, the cobalt +3 ion will have the configuration of 3d6 4s0. A glance at the configuration indicates that the complex is paramagnetic due to the presence of 4 unpaired electrons. Magnetic studies, on the other hand, have revealed that the given complex is dimagnetic in nature. This is possible only when the 4 unpaired electrons in the 3d orbital get paired up, contrary to the Hund's rule. As a result of electron pairing, 2 vacant 3d orbitals are made available for hybridization. Thus, 2 3d, 1 4s, and the 3 4p orbitals hybridize together to give a set of 6 equivalent d2sp3 hybrid orbitals. The 6 pairs of electrons donated by the 6 ammonia ligands occupy the 6 hybrid orbitals. You can see that there are no unpaired electrons left in the metal ion. Thus, the complex is dimagnetic and has octahedral geometry. As you can see, the metal ion has utilized its inner 3d orbitals for the formation of the complex. Hence, this complex can be called an inner orbital or low spin or spin-paired complex. Similarly, in the case of complex ions such as hexaamine manganese 3 or hexacyanoferrate 2, pairing takes place contrary to Hund's rule, resulting in the formation of dimagnetic inner orbital complexes with d2sp3 hybridization. Now let us examine a paramagnetic complex, sodium hexafluorido cobaltate 3. In this complex also, cobalt is in +3 oxidation state. Magnetic studies indicate the paramagnetic nature of the complex. This is possible only when the outer 4s, 4p and 4d orbitals undergo hybridization. Thus, the cobalt ion undergoes sp3d2 hybridization and has octahedral geometry. As the outer d orbitals are utilized for hybridization, the complex is also called an outer orbital complex or high spin or spin-free complex. Similarly, in the complex ions, hexachlorido manganate 3 and hexafluorido ferrate 3, the outer 4s, 4p and 4d orbitals get involved in the hybridization to form outer orbital paramagnetic complexes with 4 and 5 unpaired electrons respectively. However, note that in the case of octahedral complexes formed by metal ions, such as titanium 3+, vanadium 3+, and chromium 3+, which have 1, 2, and 3 unpaired electrons, the magnetic behavior of these free metal ions and their coordination entities is similar. As you can see, in these ions, there are 2 vacant d orbitals available for octahedral hybridization with 4s and 4p orbitals. Thus, these octahedral complexes are always paramagnetic in nature. Now let's study complexes with the coordination number 4. You know that when the coordination number is 4, the complex may either have tetrahedral geometry or square planar geometry. We will first examine a paramagnetic tetrahedral complex, potassium tetrachlorido nickelate 2. In this complex, nickel is in +2 oxidation state, and thus has the configuration of argon 3d8. The complex can be paramagnetic only if nickel undergoes sp3 hybridization and not dsp2 hybridization. Thus, The 4s and 4p orbitals hybridize together to give a set of 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in the hybrid orbitals. Hence, the given complex assumes tetrahedral geometry. Tetracarbonyl nickel 0 is an interesting example of dimagnetic tetrahedral complex. In this complex, the metal atom nickel is in zero oxidation state. Experimental studies suggest this complex to be dimagnetic in nature. This is possible only when the paired electrons in the outer 4s orbital pair with the electrons in the 3d orbital. Thus, the metal atom undergoes sp3 hybridization to result in 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. Hence, the complex is a dimagnetic tetrahedral complex. Now, let us examine a dimagnetic square planar complex, tetracyanonickelate 2. In this complex, nickel is in +2 oxidation state and has the electronic configuration of argon 3d8. Magnetic studies suggest this to be a dimagnetic complex. This is possible only when the 2 unpaired electrons in the 3d orbital get paired up. Thus, the vacant 3d, 4s, and 2 of the 3 4p orbitals hybridize to form a set of 4 dsp2 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. The complex so formed has square planar geometry. Here is a question for you. What is the geometry of the complex if the spin-only magnetic moment of potassium tetrabromido manganate 2 is 5.9 Bohr magnetons? The coordination number of the Mn+2 ion in the given complex is 4. Hence, it may either undergo sp3 or dsp2 hybridization, and may have either tetrahedral or square planar geometry. However, the magnetic moment value of 5.9 Bohr magnetons clearly indicates the presence of 5 unpaired electrons in the complex. This is possible only when the metal ion undergoes sp3 hybridization. Thus, the given complex has tetrahedral geometry. Let us now look at the shortcomings of the valence bond theory. Although the valence bond theory successfully explains the formation, geometry and magnetic behavior of coordination compounds, it suffers from certain drawbacks. They are: coordination compounds are generally colored, but the valence bond theory does not explain the color exhibited by these compounds. This theory does not provide a quantitative interpretation of the stability of the complexes. It does not give the quantitative interpretation of magnetic data. It fails to predict the exact geometry of complexes with coordination number 4. For example, according to the valence bond theory, CuNH342+ has tetrahedral geometry. But X-ray analysis has proved that this complex has square planar geometry.